how to do that. Okay, let's take a look at this one now. This one's a little bit different. This one talks about a large drug rehab center where 18 of 59 patients were found to be HIV positive. Okay, and it's asking us what's the 95% confidence interval for the proportion of patients who are HIV positive. Now, we know we took a sample of 59 patients, right? 18 out of those 59 patients were found to be HIV positive. So what percentage, what's the point estimate for the percentage of patients who are HIV positive in this population? The population happens to be drug users that go to drug rehab centers. So, it's a population that's going to have an unusually high rate of HIV. But based on our sample, what percentage of this, what's our point estimate of the percentage of patients who have HIV in this population going to be? Anybody want to predict that? Okay, 18 over 39. Okay, got somebody came up with it. Can you guys see can you see each other's type when you type into the chat window? Can you guys see the other person's chat window? Good, okay. 18 divided by 59 equals. Okay, if you want to stay anonymous and use a fictitious name, by the way, and that would make you more more comfortable about asking a question or something like that. You don't have to worry about using your real name or anything like that, since this is all anonymous anyway, since we're not tracking who's attending or anything like that. So feel free to use like a fictitious name. Try to use one from literature or something like that. I kind of like that. So, but at any rate, okay. So now approximately 30.5% of this population is HIV positive. Excuse me, I misspoke. 30.5% of this sample is positive. We don't know what percentage of the population of people that go to drug rehab centers is HIV positive, because we didn't sample every one of them. We didn't survey every one of them. We only surveyed random sample of 59 patients. Okay, however, we have the same quandary here that we had before, and that is that we're really interested in, no, we're not really interested in those 59 patients. We're just doing that because we want to really have an idea of what the population percentage is, what the population proportion. Instead of mu, we're going to call that P. Okay, so now we know that P cap, that's our population of our kind of our X bar. This is the proportion of our sample that is HIV positive. 18 over 59, which is going to be equal, I'm going to round it to 0.30. Okay, it's about 30%. Okay, so now we have the same issue here that we have before. We want to know this. We know this, but this is what we're after. Well, there's no way for us to ever know this for sure unless we actually sample everybody in the population. But we're interested in knowing, well, what if it's, I think it's 30%, but I know it's not going to be exactly 30% because I only picked out the 59 people at random. I need to know what's my range that I can be 95% certain. In other words, 5% chance of being wrong and not capturing the true population proportion within the range that I'm going to assign. What's my 95% certainty of having an interval, a confidence interval, that will capture this true population mean? And we're going to do that the same way we did it before, except that this time we're going to take P plus or minus. Well, now in this case, we have an interesting quandary here. Okay, and that is that, do I use T here or do I use Z here? Well, one of the rules that we're going to set up for working with proportions is that each side of this proportion, whether it's P, right, have HIV positive, or whether it's 1 minus P, which is all the people that are HIV negative, right, each side of those has to have a sample size of at least 15 or greater, equal to or greater than 15. Okay, well, in our case, we had 18 people that were HIV positive, and then you have 59 minus 18 that are HIV negative. Okay, so we satisfy that criteria. Well, that means if you satisfy that 15 on each side, then your sample size is always going to be greater than 30. And you guys may remember that one of the rules that we made up, kind of a loose rule that we made up before when we were working with these other distributions, is that when we looked at the t-table, let's see if I can't find it again. Oops, not that one, not that one. Here, when I was at the t, here we go. When I looked at the t-table, I noticed that when I had degrees of freedom 10, then I was working with a t-score of 2. Degrees of freedom 4, 2.7, 8, 2.3, 14, 2.1, 20, 2.06. 28, 2.04. Well, by the time I get to 30, I'm at 2.04. I'm getting closer and closer and closer to that 1.96 for infinity. I never really get there until I get to infinity, but you know, most statisticians feel that if the sample size is larger than 30, that they're willing for most purposes to use the z-score instead of the t-score because they're so similar as the sample size gets larger. So if we get over 30, we have a sample size of 40 or 50, right? We're close enough to the value of t converging with the value of z for a 95% confidence interval that we're willing to say, well, let's use the z-score instead. So in that case, since we already have a rule for our proportion, that the sample size of each side has to be at least 15, so you know that overall you're going to have at least 30 people involved in the study, well then we're probably not going to use t at all here. We're always going to use z for alpha over 2 again for 5. If this is a 95% confidence interval, alpha, our acceptable level error is 5%. Okay, if it's a 99% confidence interval, then alpha is equal to acceptable level errors at 1%, and alpha over 2 is equal to 0.005. Okay, and you would look up on a table what that area is over there. I think it's 2.64 or something like that, or maybe bigger, right? So we're going to use the z-score instead of using the t-score when we deal with proportions, as long as we meet that rule, that criteria about sample size. So plus or minus z-score times the standard error. Well, how do we calculate the standard error for this? The standard error, Ben, if n is equal to 30, we use the z-score instead of the t-score. Okay, even though it's not going to be exactly the same. But in the case of proportions, it's each side has to be greater than 15. In other words, in order to have a proportion that would meet that criteria, let's say that we had 30 people, and 15 of them had a disease, and 15 of them didn't. 15 of them had a disease, 15 didn't. So 15 out of 30 people had a disease, 15 have it, 15 didn't. So you have a sample size of 30, right? So even it's 15 on one side, 15 on the other. On the other hand, if you had 30 people and 10 of them had the disease, 20 of them didn't, and your proportion would be 10 over 30. Well, problem there is that this side is less than 15, so we can't do that. We can't assume to use the standard use this to calculate standard error. In our case, we have two sides. We had 18 out of 59. So you have 18 people that have HIV, and you have 59 less 18, which I guess is 30. What is that? 30, 33. Excuse me. Hang on a second. 18, 30, 48, 30, 40, 48. That's be 41. You have 41 people that don't. You have 18 people that do have HIV, 41 that don't have HIV. So your sample size is actually 59, and both of those values are above 15. So in order for this to work, you're never going to have a situation, since you have to have both sides have to have 15 at least, you're never going to have a situation where your sample size is less than 30. Make sense? Okay, a little confusing, I can understand that. Okay, so let's see what we got here now. Well, how are we going to calculate standard error? Well, the standard error in this case is going to be calculated using that proportion. Standard error is equal to P times 1 minus P over the sample size, and we take the square root of that whole value. Okay, so in our case, standard error is going to be equal to 0.3 times 0.7 over 59, and then we're going to take the square root of the whole thing. We're going to do the square root last. Okay, so now let's get our calculator out. Okay, and let's see. We got, let's see, 0.3, whoops, 0.3, try this again. 0.3 times 0.7 is equal to 0.21. I'm going to store that in memory. Okay, and let's see, and actually I don't even have to. 0.21 divided by 59 is equal to 0.00355, so on and so forth. I'm going to take the square root of that, and my that value, this value for standard error, is equal to 0.056, 0596. I'm going to call that 0.06. This is equal to 0.06. Okay, so my confidence interval is going to be equal to P cap, which is 0.30, plus or minus my z-score, which is 1.96, times my standard error, which is 0.06. Okay, so let's see. That's going to be 2 times this, which is going to be about 0.12. So it's going to be 0.30 plus or minus 0.12. You guys would actually work that out and not round off until you're all done when you do your work. Okay, so that's going to be, it's going to be from 0.18 to 0.42. Pretty wide range there, right? Okay, everybody agree with that? Everybody comfortable? Did I make any errors there? Okay, so that's our confidence interval. Okay, again, which of these is our point estimate? Point estimate is 0.30. Which of these is our margin of error? Okay, our margin of error is 0.06. That's how much we're adding and subtracting to these values, right? Okay, good. So now let's take this one step further. Okay,